The oxygen enhancement ratio is LET dependent, like I said before. So just here's another graph showing the same thing. So it's about 2.5 for diagnostic radiation, decreases to 1 for high LET. So there's actually a little bit of a lesser effect of the oxygen enhancement ratio for high LET. The next thing is the phase of the cell cycle. So here's a graph of the cell cycle, the radiosensitivity with age, tissue with high metabolic activity, so young and dividing cells and tissues are more radiosensitive than mature cells, and so this is why basically there's great particular attention paid to radiation safety for children and pregnant women, because young people are more sensitive than older people to radiation. The cell type, cells contain lots of different molecules. Some of the molecules, there's a lot of them, so if there's radiation damage to these molecules, there is a lot of spare ones to replace them. But some molecules over here are less abundant in a cell. Therefore, radiation damage killing off a few of these molecules can have a greater effect on the cell. So the type of cell is radiation dependent. Alright, the next thing we'll look at is what's called target theory. So target theory is based on the concept of a sensitive key molecule. So in this, let's assume that for a cell to die after radiation exposure, its target molecule has to be inactivated. So let's say the target molecule for us is the DNA, but it could be something else, but we'll just stick with DNA. So there's a few different models, mathematical models. So we'll go through a couple of these. So let's have a look at the single target, single hit model. So for this model assumes that within each cell there's a single target that has to be hit by the ionizing radiation once to cause reproductive death. So let's start with 100 cells, and we'll have a random hit pattern. So after one hit, so we have one radiation incident on 100 cells. So let's say it'll hit one of those cells and kill it. So that was after the first radiation. So then we send in a second, say X-ray, and then on the second hit, there's a 99% chance that it will hit a different cell to the one that the first cell hit, and it's a 1% chance that it'll re-hit the first cell. And so as we increase the radiation dose or increase the number of X-rays, this is going to change and change and change. So as the number of hits increase, it's going to be more probable that a given cell will be hit twice or more, but you only have to hit the cell once to kill it. So as it increases dose, it will have a slightly less probability the more dose that you put into it. So the random hit pattern is described by a Poisson distribution. When the number of hits is equal to the number of cells, 63% of the cells will be hit at least once, and 37% will survive. So that's doubling up. So randomly, if you send in 2 radiations, that means that one cell has caught both of the radiations, which spares a different cell. So this is a single target, single hit model. Here's a figure. If we have 100 squares here, and we're talking about if raindrops fall on it. I don't know why this plane is there. I don't know. I think I'm not sure why they put a plane in this, but there you go. Right. After the irradiation of 1,000 cells, the dose-response relationship becomes exponential. So we plot it on a semi-log graph, and we'll have a surviving fraction versus dose in this graph. So it's semi-log. We can come up with an equation for it because it's a log, so it's just a exponential or inverse exponential, and we've got mean lethal dose. We've got a D0, we've got a D. It's just a very simple exponential explanation. When D0 equals D, the cell survival equals 37%. So that's 0.37 always comes up in exponential graphs. So that's called the D37 dose, and that's a measure of radiosensitivity. Alright, what if you give a group of cells two D37 doses? Well, after the second lot of dose, it will be after the first lot, it will be 37% survive. After the second dose, it will be 37% of 37%, so that'll be 14%. The next thing is a multi-target single hit model. So this is an old model, and it assumes now instead of a single target, you have to have a target that has to be hit. You have to have multiple targets, which will all need to be hit once. So each cell has got multiple targets in there, each of which has to be hit once, and so inactivation of the target with one event is not lethal. So the first few hits, it's pretty unlikely that damage is going to be done to cells, and so it normally takes quite a few hits before the damage is actually done. Now, so if we look at this model, we'll get this equation here and this plot here. So that's what we get, and we have this little shoulder up here, and a long exponential down there. At low doses, there's nearly 100% survival. That's because each cell is very unlikely to get multiple hits with just a few doses. But as you increase, you'll start to, after a bit of dose, or I should draw it there, you'll start to get more and more cell kill. The mean lethal dose is, again, it's this 37%, and then there's this threshold dose up here, DQ, which is where it starts to go from the shoulder area down to the exponential area. So that's the threshold dose. Here's some doses for various experimental mammal cell lines. The D0 and the DQ, so you can see that there's quite a bit of variation between different cell types. The linear quadratic model is a current model that is being used, and this is the preferred model, and this has there's two components to the cell killing. One is due to single event killing, so double strand break caused by a single ionizing particle. The probability of no damage is either minus alpha D. Then there's another component which has a two event killing, so a double strand break caused by two separate ionizing particles, and the probability of no damage is e to minus beta D. So we've got this alpha and beta D squared, I should say. So we've got this alpha and beta here. So we've got the model is e to the minus alpha d minus beta d squared, where alpha and beta are constants, and they depend on the tissue type. So this relationship has an initial zero slope, which is in agreement with the experiment, but results in a continuously bending curve, which is may not actually be accurate. All right, that's it for the biological component, and we'll next move on to part 3, which is the deterministic effects.